Hey everybody, this is Larry. This is me going over Q4 of the weekly contest 362. String transformation. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this problem. So just a little bit of heads up, the live portion about this, it took me about an hour and 10 minutes to solve this problem. So yeah, that live portion is long, but the explanation should be a little bit shorter. Feel free to kind of skip through it. Though today, for some reason, I was way talkative during this problem, so I think it affected my time in that I think I was solving it slower, but hopefully it is also useful if you watch it in a fast speed. Okay, so what is this problem? So this problem, there are multiple components, and that's kind of part of what makes it tricky. And I like to explain the solution, but also to try and just go over my thought process in the contest as well, just to kind of, because I think anyone can understand the solution, but try to figure out a way to get your mind in a way such that you can come up with these solutions next time, or maybe 2 times or 3 times later. That's the hard part, right? And that's what I try to do, and that's why I don't just go over the solution, because the solution is easy to understand at a certain point, but easy to understand does not necessarily mean easy to come up with, right? And all that being said, I did know the overarching of what I needed to do for this particular problem, but it still took me a long time. And we'll go over each of those components in a second. But the first thing that I did during the contest, to be honest, is that I think I got a little bit lazy during this one. I mean, it's not always lazy, but for this one, but I think like most people can actually benefit from this as well, is to write a brute force solution. So I wrote a brute force solution knowing that it wasn't going to pass, because you look at the constraints and K is ridiculous, N is also ridiculous, so I knew brute force wasn't going to pass, but I wanted to see if I could maybe figure out the pattern for the number. And it took me a little bit of a while, but I wasn't able to see it, to be honest. Or like, I was able to see some patterns, but I wasn't able to generalize it. But I was able to kind of be like, okay, there was some, but it gave some credence to what I was going to do next, which is that I was going to try to figure out dynamic programming. And actually in this code, I actually did do it with dynamic programming. So we'll go over the dynamic programming solution first and kind of go through it, right? And I'd like to draw it out, but I think I'll draw it out for this one, because people always complain that I don't draw enough. And I guess I did spend money on this drawing pad, so hang on. At some point in the past anyway, maybe not anymore. Well, I guess you don't keep on spending on, so I don't know. Did I like turn off my keyboard by accident? Okay, I did turn off my keyboard by accident and drop the pen. Got my drawing pen. Oh, okay. Sorry friends, that took a little bit of time. Hope you fast forward through it a little bit. Alright. So why do I have 2 setups? Okay, so basically the idea is, okay, it's just thinking about the number of, to split it up, right? Instead of thinking about only the answer being the number of combinations, how did they say? The number of combinations of operations that gets you to match S and T, right? So it's to kind of set it up so that you split it up into the number of combinations that match and the combinations that don't match, right? So I'm going to denote it with F of. This is a little bit weird. I don't know. That's a very terrible F though. So F of. So let me rewrite this actually. So yeah. Okay. Let me just write it this way then. Hang on. F of x is equal to the number of this one. Maybe I should have drew out number of ways. Maybe this time I didn't have to. With number of correct ways, meaning S is equal to T, after X moves, right? people always wonder why I don't write these. Now you see why. And maybe another h of x, where h of x is equal to number of incorrect ways. And incorrect just means and incorrect just means that they're displaced, right? That means that it is a rotation, but you know, I make the distinction because there's one test case where s is not equal to t, and I just forgot about it. I mean, I thought about it when I first saw the problem, but then I forgot about it after there's no rotation, and then that was the wrong answer. But yeah, so that's, you know, it's very hard to draw on this thing. So anyway, so let's say I have these two things, right? Well, so then the idea here is to kind of calculate. The idea is to calculate the number of moves between the transitions, right? Because then now here you have f of x, and you have h of x, and you have maybe f of x minus 1 and h of x minus 1, right? So this is the part where the string problem comes into play, and without kind of going into it too deeply, we'll do an example. I mean, we'll go over it deeply later, but for now we won't go over the mechanics. But let's just say, you know, for example, let's say we have a b, and then maybe some ba. So then now, right, what happens? So there are two rotations that makes it good, because, you know, there's excuse me. Hopefully this makes sense. But let's say this b is index 1. So there's one where b goes to this one. And then the second one that goes to b is equal to this one as a prefix, suffix, or whatever. So there are two rotations that are good, right? So what does that mean? What can we do from this? That means that, okay, so here, f of x, changing colors. Number of correct moves. Well, if we had correct moves before, and remember now, given that we have some number n, right, is the number of characters in S, that means that we have n minus 1 moves, because we can not go 0, it has to go 1, 2, ... all the way to n minus 1. So that's going to be n minus 1 total moves, and so you cannot go 0. So then what does that mean? That means that if if you were in a correct position and you cannot go 0, that means that there is number. So that's there's good minus 1 ways of getting here, right? Where good is equal to the number of good ways, right? Hope that makes sense, because and here there's good number of ways here, because you can always get to one of the offsets, right? By using good number of ways. And good minus 1 is because you can't stay at 0, and because you're already in a good place, then yeah. And then in the other way, if, and this is just dynamic programming, I hope you see the structure now, if you want to see the number of correct or incorrect moves here, this means that the number of bad ways, right? So because you're already in a good, all the bad ways is going to be good. So you have bad, right? Yeah. Because 0 is going to be a good move, so you take away 1. Here, this is actually bad plus 1, right? It's bad plus 1 because if you're winning a bad move, as long as you don't take any of the good moves, you're good. You can get here, right? And yeah, maybe I messed this up. Did I mess this up? No, I think we're okay. Yeah, I think this is right. So basically, that's the transition, right? And yeah, and so we're going to shelve this for a little bit. This is the transition for a number of moves, and this is I wouldn't say this is basic dynamic programming, but this is like a, let's say, intermediate dynamic programming. If you, I think like if you are given just this particular part of it, so maybe with a smaller k or something like this, I think maybe is a tougher interview question, but it's still gettable. Keeping in mind that this problem is an 8-pointer, it's structured to be a pretty hard problem. So this is only one of the components, and if you got this one, you're already ahead of a lot of people, to be frank, I think. You know, just try to figure out the transitions of number of ways, and of course, the good ways we'll calculate later, and bad is just equal to, the number of bad ways is just equal to n minus 1, which is the number of moves, minus the number of good moves, right? So that's the number of bad moves, so bad plus 1 is because you don't have to worry about, or maybe, I think I messed this up. Actually, this is bad plus 1 because you don't have to worry about the good move, and here you just have the number of bad moves already. Yeah. So I guess I didn't really need to draw that, but hopefully, for people who ask me why I don't draw enough, hopefully this is a good illustration. And then the second part is about, or maybe even the first part, right? Is about the string thing, right? How do you calculate the number of overlaps that are correct? So there are a couple of ways to do this. Actually, I'm going to bring back the drawing board. There are a number of ways to do this. But they're all kind of string matching related. Right? So let's say, and there are a couple of, like I said, there are a number, where'd my pen go? Huh. Did I just lost my pen? Oh no, there it is. So, yeah, so there are a number of visualizations, but I think implementation-wise it'll be similar. But one way to think about it is that you could double the string and just count the number of sliding windows. In that case, you can use different things. For example, if you have let me change it back to black. For example, if you have ABC, you could double the original string and then just, you know, do a comparison on, say, BCA, and then just kind of slide this around, right? And this, of course, is going to give you the count, and yeah, and you could use, you know, KMP or something like this. The way that I actually did it is with Robin Kopp. I'm not going to go over Robin Kopp too much in this particular video because there's a lot of things to go over. But basically, it's just a substring search algorithm, right? So, you know, there are a lot of these, and you can kind of figure it out. With the string doubling, with Robin Kopp, you can also do, you know, it's basically also known as rolling hash for that reason, is that you have this sliding window of hash, and then you just kind of match, you know, all of it, and you can implement it in a couple of ways. So this part is actually not that bad if you have done it before. If you haven't, then it is, you know, it is still tricky, but this allows you to do the Robin Kopp, or the get the count. And then now that you have get the count, there's another difficult part. The difficult part is that, oh yeah, and you need something like a Robin Kopp because n is 5 times 10 to the 5th, so you can't do anything like n square, because if you do something like n square, well, that's going to be too slow. But if you do Robin Kopp with a sliding rolling hash or whatever, with KMP or either as well, that's going to be linear time, and that's O of n, which is going to be fast enough. Otherwise, you can do the dynamic programming, right? Well, no, because as it turns out, okay, wait, let me step back for a second. So after that, now you get the total count of the number of good positions. So then now you can plug into the dynamic programming setup that we have, where we have good and bad and n, and then you know, that's the number of paths for transition for each of those things, right? And then after that, you ask yourself, okay, I have my DP, I'm good, let's submit, right? No, wait a second, K is ridiculously big. So if you write it as a dynamic programming thing, and if you have that transition formula, you could do it in O of K, the O of K plus n, and O of n to kind of do the string matching, and then O of K as to kind of do, you know, to go through each of the K of the transition, right? So it didn't really end up that way because K is ridiculously big. And because K is ridiculously big, we have to rethink how we do it. Let me actually go back here for a second, right? And the way that I would think about, there are a couple of ways you can think about it. The way that I'm thinking about it is with something called a matrix matrix exponentiation, which is a really tough way of saying it. I mean, there are actually other ways of visualizing this as well. I'm not going to get into it because for me, I think this is a little bit easier to understand, but or at least like fewer things to come up on a contest. Of course, I think if you are starting from scratch, technically you could do some sort of things that are similar to like binary lifting, which we did last week and 2 weeks ago. Something similar to that idea of just like, you know, taking these components of move and figure out the transitions in a way that it combines them. But yeah, but let's say, for example, you know, so let's say we have some f of x, right? Oops, and some h of x, as we said, right? And we're going to write this as a set of equations, right? So f of x, as we said, is going to be f of x minus 1 plus or times the number. So f is the good one, so it's good minus 1, right? Let me. I think black is fine, right? So it's this times this plus h of x minus 1 times good, right? Maybe I'll just let me rewrite this. Let me define this a little bit differently. So, so G is equal to good, right? The number of good positions that we have, and good are just the number of positions that are matching. That's a terrible handwriting, but that's why I need to do less of it, right? Oh. And then h of x is also similarly, and as we said, you know, number of moves that we can do is n minus 1. So bad is just n minus 1 minus g. So going from a good state, how many states can you get, right? Well, it's just the number of bad states, because every bad state will get you to a bad state. Yeah. Yeah. This is bad, which is n minus. Oh, what the? What happened there? And then for bad states, it's the same idea. But now, to get from a bad state to a bad state, you also you cannot make move 0. So now you have n minus 1 minus g minus 1, right? So, yeah. Something like that. Why that? This is a little bit awkward. My code is a little different than that. Yeah. Maybe I'm off by one by here. I may be off by 1, but this is just the idea, right? Yeah. Am I off by 1? Sorry, give me a second. On a bad say. Let me. Oh, this is this. Oh, this is. I see. This is this minus 1, so this is this plus 1. Okay. Yeah. Okay. I think I forgot the parents, so that's why I got confused on the parents. Because now there's one. Because if you cannot, there's 0 state, so the reason why they're different is because you're trying to take out the 0 state. The 0 state, meaning if you move 0 moves, is a bad. Like if you stay in a bad move, so then you have to do one. Yeah, so that means that one of the moves are going to be bad. Yeah. So that's basically the idea, and And it turns out you could write this as a set of linear, and this is a set of linear equation if you structure it this way. So you can actually just write the matrix like this, right? You can, and if you expand it out, and this is based, I'm not going to go over matrix multiplication too much, just because there's a lot of linear algebra background that goes into this. But basically, you can literally just translate this into a matrix. Though I think I translate this incorrectly, so maybe you can't. But that's basically the idea. This is matrix that, and then once you kind of make sure you have your index correct, and you, because now if you do it k times, it is just this formula expanded out k times, and it turns out that that formula expanded out k times is just equal to this matrix times k, right? Oh, sorry, I said it wrong. This matrix to the k power, which is how we got the matrix exponentiation. And the reason why this is what we want is because now you can actually do, repeat squaring to do it in log k time. Instead of O of k times, you can do it in log k times, which is going to be fast enough. That's basically the core idea behind this matrix multiplication, matrix exponentiation. Yeah. And then the only remaining part is just setting this up, the base case. And it turns out, and there are really two main cases, right? One is if it starts out the strings being the same, like exactly the same, so it's one of the good states, and the strings being not the same, which is one of the bad states. And it turns out that there's a easy interpretation, which is f of 0, right? So f of 0 is... f of 0 is, of course, as we said, is equal to the number of good states, or number of good states given 0 moves. And of course, so if they're equal, then this is 1, and then h of 0 is going to be 0. Otherwise, if they're not the same, then f of 0 is going to be equal to 0, because 0 of them are correct, and h of is going to be 1 because your initial one is 1. And of course, you can kind of visualize it as just multiplying it by a vector of whatever, f of 0 and h of 0. And that's basically the idea. I kind of this is not a difficult concept once you've seen it the first time, but it's also not a easy concept, just to be clear. And keeping in mind that we put like 4 things together already, we had to learn how to do rolling hash. We had to do dynamic programming to come up with the recurrence, and then matrix multiplication and exponentiation, and also keeping in mind the mod, which means that you have to write your own matrix exponentiation and multiplication. Because at least NumPy doesn't do the mod part anyway. So yeah, that's basically the problem, and we'll go over it now. And actually, I did actually write the dynamic programming solution just so that I can verify the answer, because I wasn't quite... yeah, it just took me a while to figure it out. But yeah, and first of all, so I did the rolling hash. You may ask me how did I get a big prime. I just googled a big prime, and this is the first thing that came up. So I don't know. It doesn't. I mean, it can be challenged, but on Leetcode it doesn't matter as much, as far as I know. If this fails system test, I'll be very sad. But yeah, and this is just the rolling hash stuff. I'm not going to go over it too much, but yeah, this is the rolling hash, and then this is the rotation of the rolling hash. So yeah, I'm not going to go over it in this particular form. I've done it in the past, but I'm just going to write that this is Robin Cobbs, so if you want to look it up. And of course, this is O of n times and O of 1 space, I guess, actually. Right? And here, we just keep track of the number of counts that the rotation is equal. That's our number of good states, so to speak. Yeah, and also we terminate early. If we have no good states, it means that there's no answer, so we return 0. It cost me a wrong answer, so it is what it is. Otherwise, I kind of wrote this different in a weird way. But basically, this is just saying the initial state is S is equal to T. So, or are they different? I don't know why I wrote it. I kind of, yeah. I think I just wanted it to be this way, and for reasons that I confused myself during the contest and why it took so long is that I kind of mixed the order, because for me I thought, oh, same as you go to this thing, so then the first element is going to be h of x, and the second element is going to be g of f of x in the same notations that we had, but it also just means that the number of incorrect ways or our place ways and number of correct ways, because I don't know, that was my notation, but I can't confuse myself. And again, here good is equal to count, bad is equal to n-1 minus count, and so here are the transitions, things that we said before, right? I think I actually yeah, the way that I think I did the multiplication or something wrong here, so don't hold me to this one. Yeah, I think I actually did this wrong, but it's consistently wrong, so it's fine, because I think my multiplication was also wrong. So I think this is supposed to be, yeah, why did I do it this way? I think that's why I got this wrong and kind of had to, right? I think this is the way to do it, and I think in this case, then now, yeah, I think that's why I kind of did it a little bit weird. Okay, maybe not. I don't know. Don't know why this is a little bit weird, but maybe I just missed that. But in any case, that is my transformation matrix, right? This is kind of what we talked about with respect to that, and then now we have to do the MyPow. But yeah, here we did the MyPow. This is standard matrix exponentiation. Let me type that up. Matrix exponentiation. I can't exponentialization. Is that the word? Exponentialization. Okay, there you go. Right. So it's that, and this is going to take O of log k times, and technically, and the cost of the multiplication. But we have 4 elements, so I'm just going to keep it as 4, which is a constant. So log k times. Right, and this is standard stuff. I'm not going to go over it because this video is already pretty long. So yeah, and then this is also matrix multiplication. Like I said, maybe, hopefully, did I fix it? Okay, I think I fixed it. But if this is wrong, do it yourself. But the reason why I didn't use NumPy or whatever is because I have to do the mod part, which is the trick. This is why we have to do all this ourselves. And yeah. And then I convert it to an array, and I do a dot product, which is basically, to be honest, just this multiplied by this, and then you get the answer. And like I said, the number 1 is the element. So you get 2 counts, right? One is the number of incorrect position counts, and the number of correct position counts. We want the correct position count, so it's number 1, and then we have to make sure that, I think. Yeah, and then we have to make sure that it's just mod. I think we don't need to do the mod in this particular here, but it's okay. And yeah, and that's basically the idea. And what's the total complexity, right? Well, the hash, like I said, it's going to be O of n. The matrix exponentiation is going to be O of log k. So it's actually going to be O of n plus log k. And of course, k is the number, oh sorry, log k is the number of bits. So this is actually linear time, right? And yeah, and you can actually also see that I did it with, and I kind of double checked it for a lot of random cases, or maybe not a lot, but a few anyway. Here, this is how I do the dynamic programming. So if k was smaller, you could have just done the dynamic programming in this way, and that would be good enough. The good and the bad is the same thing, and you can kind of see how I structured the matrix. But actually, because I wrote this like this, I actually confused myself, so I kind of wrote it in a really weird way for a little bit. But yeah, I think what I needed to do was actually, yeah, well, but yeah, but that's basically the idea. That's the problem. And like I said, there are like 4 different problems in this problem. It makes it very hard. Let me show again the Robin Carp, and then the matrix multiplication. Though this part, like I said, it's not. I just typed it up off my head, so I think it's a little bit off. But it's off consistently, so if it's off, then let me know in the comments, but it's off consistently, so it should be right. And then here's the DP if you want to curious about that. And keeping in mind to kind of not forget the mod, and also the count is equal to 0 that I got the wrong answer from. I actually did get a wrong answer from this one because I had it transposed once, and it was just not giving me the right answer for a big case. That's all I have for this one. Let me know what you think. The explanation is half an hour long because this is a hard problem. So hopefully you hit the like button because it's tiring just even go over it. So yeah, let me yeah. Anyway, you could watch me solve the problem live next. 3, 4. All right, let's go. All right. I bet someone did max flow and just did it very quickly. Just copy and paste it. Alright. Anyway. Remove suffix s of length L and append it to the beginning of the s. Okay. In one operation. Alright, mod. Okay. Mod. How many people have solved this? No one so far. Is a little bit tricky because usually, you know, you could see people solving it, and that's just it is what it is. But and usually people are ahead of me. That's why what I'm saying. In exactly k operations. What? K, K is the number of operations. You can choose any of length L. Can you just okay? Can you choose 2? Oh, it has to be not 0 or n. Okay, that makes sense. Huh. This one may be a tricky one. Which would. Even without, how do I even do that? And k could be pretty big. I mean, it's probably, it just comes down to exponentialization. That's too much of a hint. If they have kept it small, it may actually have been interesting. But then the question is, okay, so let's say we do all the matchings. So then you get all the indexes. And then what? And then it is the number of count that. This is too hard. I feel like I have an idea. Ooh, someone got it. I feel like I have an idea, but it's too hard. I mean, if it was someone to get it, it would be someone like Uri. But so, it's an 8-pointer. I don't think. Maybe I'm not getting this one, to be frank. Okay, let's say we have all the indexes. How do we get it? I guess in one turn you could get it, and then how does it get in 2? 2 would just be the summation, or the number of counts of 2 numbers summing to each of the counts on k. I think the duplicates is not as interesting. It's a little bit tricky because for this one you have to subtract out the. Because 6 is a case, but it's not a case for k is equal to 1. Right? But you have to make sure that, so, because then if it's k is equal to 2, then how do you do it? Let's just say we have a random string, right? Let's just say we have a random string. That there's only one case, so then k is equal to 1 is going to be 0 or 1, and then k is equal to 2 would be n, because it's just n ways to add to that number. And then what's k is equal to 3? K is equal to 3 is equal to is it n? It is n because it is going to be that number mod whatever. I think it's n. Maybe n minus 1 or something, but about twice. Is it 2n? What is n is good? Okay, I guess I don't even need a big number, right? I can just try some small case, right? All right, let's brute force the small case real quick. Right, so for k is equal to 3, s is equal to, I don't know, abc, it doesn't really matter, t is equal to abc, right? What would brute force look like? Brute force would look like breadth search. Right, let's do it. Yeah, let's just do it. I don't know. This gets exponential pretty quickly, but so soon. And then we can move n times, right? And next is equal to now substring plus now, right? Except it cannot be 0, so okay. And then yeah, next d plus 1, right? This is very lazy, of course. If d is equal to k, we add count and then we continue, right? Whatever, so I don't return it later by accident. So this is brute force for this. So I have 8, right? So this lets me calculate right? So then now I can try calc stk for k in range of 5, say. Actually, I don't even need to do that. I can actually do that a little bit smarter by bucketing. Yeah, I could just return, let's say, and then just collections.counter. All right. I'm just trying to find a pattern is what I'm doing in case you're wondering at home. Okay. I guess now then I don't have to do this. I can do say up to 5 or 6. Let's see, right? I did not do it. Link plus d is equal to k plus 1. How is this not 1? Did I made a mistake? Maybe I did. So this is here. Why does it not append? Oh, so it does stuff. Oh, I return because I'm an idiot. Okay. So that it skips the print statement. Alright, so it goes this would be better if it's sorted, but it just seems like it doubles every time. Right? Let's see. So 0 is going to be 1. I mean, maybe we're off by 1 because I don't think you could do... I guess 0 makes sense, actually. 1 is 2 doesn't make sense necessarily. Oh, I'm just being dumb. Okay, of course this is 2. What I need to do is count not just k, but... yeah. Well, if now is equal to t... No, what is now? Okay, t. Okay, I am an idiot. So lucky we checked that. So 0, 1, 2. So 1, 2, 2, 6, 10, 20. Okay, that is an interesting pattern, isn't it? Now, let's do it up to 10. Right. And let's put it in a better way. And let's just have one test case because it's not a real test case for now anyway. Tell me why? How am I forgetting semicolons? Am I a noob? The answer is yes. Okay. Does this pattern look familiar? It feels familiar. Let's see what happens with BCA then. And that changes a lot. Does it? Actually? Let's see. Well, okay, just change by 1. So that's good actually. That means that there's something to this pattern, and I'm not gonna lie, I'm gonna OEIS it. Ah, 342 typo. I'm actually surprised. This feels like a thing, but apparently it is now OEIS. That is actually surprising. Unless the one of the cases don't matter. I mean, it's the expansion of... I mean, I found it, but so I think the 0 case is kind of wrong. I think that's why. But okay, so what do I do with this OEIS? Also, the formula is just this. I feel like, and you know, in case you're wondering. And I feel, I guess really smart people really didn't know this, but how many people got 5, 6? 35th, not great, not bad. Okay, and then of course, if you have duplicates, so let's try something real quick while we still have this brute force, ABAB, right? Oh, well, the second time it doesn't matter. Oops. Of course, it doesn't print anything. So this is still looking the same-ish, except that it got shifted. So it's just from the, well, I mean, I guess it's just the same formula, but just the number of times in the beginning. So, and of course, this formula is you can use with a Q matrix, which is ridiculous, by the way. This is a lot of stuff to do. Like, obviously, because if you do it with K, then this is going to be too slow, and I'm talking too much and not coding enough, to be frank. But okay, so let's actually try like this one, right? So there are 3 ways to do it. So what does that mean, right? That means that I probably ran too big for 10. I forget what the numbers was, but let's try for 8. Yeah. Is this the same? This is 2, 2. Not really, actually, right? Let's change this off by 1 for a second. So the case where there's only one instance, this is true, but maybe not. Maybe I was wrong on my thing, on this thing. I guess off by just a little bit. And this one maybe it just times out or something. I don't know how. Or maybe my code is bad. I don't know. Okay. So it's not always that formula, because you can. So we have to figure out how to actually solve it. Definitely, it's giving us a hint of some sort of recurrence, and I think from this recurrence, we have to create a Q matrix to solve, which is which is why we play around with this, I guess. Right. So if they're all distinct, then you have this pattern. Yeah. Did I mess this up? Why does this feel a little bit different than I had before? What did I have before? I just have ABC. What did I have before? I guess I did have just ABC before. Huh. And just ABC gives this pattern for this thing. But this is not the same pattern for ABCD, right? 1, 1, 3. Yeah, so we have to figure out how to be smarter. It's not sufficient. I thought that maybe there's some summation thing that we could get a pattern on. So I was very wrong. And even if we do get it, we have to do some Q matrix things. Wow, if I had not gotten that silly mistake. I don't know that I get this. Right, so without loss of generality, maybe I can just use the exact case. What if I let 0 be a thing? What would that? Maybe that gives me a pattern that I can recognize. Huh. So then there is some subtraction with that I think I'm just trying to do, right? Because this is just powers of 4. So that did I understand? So because this is just all right, what? Oh, if you can move 0 times, then it is just the powers of 4. So this is just and there's some trickiness here. There's no one move, so it's 1, 0, 3, 6. Maybe that I just don't get this one. Is that always just one? I guess on the odd numbers. And then for 3, it is this thing. And then offset is just subtracted from 1, so that's fine. I'm always worried that I'm gonna hit submit by accident, but alright. So, and this is just f of x minus 2, something like this, right? Something, I don't remember what it was, but oh, it's plus, but is there some wisdom in this? I see. Because it's basically saying, what is this? This is the number of ways to don't know that, like, if it was subtract maybe? Alright, let's see if I figure a pattern. What if it's 4? If it's 4, I don't think this makes sense though. Like this is, if this is 4, is something like this, I think. How am I going to come up with that? Alright, let's think about it, right? So, I think I've been trying too much to kind of play around with the formula, but let's think about it for a DP kind of thing, right? So DP of 0 is just going to be, so 0 moves is going to be, doesn't matter, or 0 or 1, dp of 1 is going to be just a number of ways of doing it, right? In this case, dp with 1 move, this is 0 actually. dp of 2, and this is, I guess, technically 1 if it's the same. dp of 2, like I'm just looking at this and how do I even derive, right? With 2 moves, it could go 1 and 3, 2 and 2, 3 and 1, so that's 3. But how do I derive that, right? So it means that okay, maybe I need to derive, right? So number of ways where this is true, where it is already equal to is equal to 1, is equal to 0, right? And then after 1 move, how many ways is there to get from here to here? I think that's the way to do it. So from 0, it can take true is equal to, in this case it's 3. Oh wait, no. In this case it'll have to be not on. So, and there's 3 ways to go here, but this is 0. So this is 0, and then dp of 1, 0 is equal to the number of things that are on and you're forced to go off, and so that's going to be 3. So that's 3 because there's 3 possibilities. And then now okay, I think I have the idea. I don't know if this is right. And how many people are getting it so far? 17 people. Some smart people. So dp of 2, okay, so then that's, you know, what am I doing? So 2 where it is true is just equal to the number of ways here, and each of them goes to each of the 3 incorrect ways. We have exactly 1 way to do it, so this is 3. And then this is just the number of correct ways to go here, right? I mean, it doesn't matter because this is just 0. So then now this is also 0. Is that true? That's not true, is it? No. This one is wrong, because this can also be correct. The correct is from here, but this can also go to here. So what is this cell? That means that for each one here, there's 1 way to go correct and 3 ways to go incorrect. So this is going to be 9. Right? Or 6. Oh yeah, there's only 3 total ways. 1 of them is correct, 2 of them is not. And the sanity check is that sums to 9 because you only have 3 moves every time. So yeah, okay. And then now the correctness is just this times 3 because, oh no, it's just this because that's the number. There's only 1 way to get here, and then 3 of 0 is equal to this. There's only 1 way and then 2 ways, so it's going to be 3 plus 12, which is 15. And this, is that true? Each of these incorrect things, there's only 1 way and then the other 2 ways, so this is 12 plus this, and if it's correct, each of these have 3 ways, so it's 9 plus 12 is 21, and this is 27. Okay. Okay, I think I get the idea now. That was a pretty sloppy, but oh, that took a long time because I was trying to figure out a shortcut. Okay, and I know that this isn't quite sufficient, but because k is big, but let's do it the naive way first, and then we'll figure out how to do the exponential part, which is not bad, but okay. Okay, because you have to set up the base case, so that's the thing, and you do it with modular math, I suppose, which is a mess. I mean, yeah, I don't think there's any way to go around it. Let me see. Okay, I mean, I think it's just modular math, I suppose. How long do I have left? 45 minutes? Oh, not this smart. Okay, 4. Okay, so then now for current is equal to 0, current v is equal to, I don't know, times, oh, it is a thing, so plus big mod, whatever. Maybe we even use the same mod, but I don't know. Let's do 10. Okay, whatever. I just googled a random prime. Okay, that's good. And then now, okay. What's it called? What is that algorithm? Whatever, just current then. S hash T hash 0 0. Okay, so now we start, and then now we do rotations. So yeah, and then what's it called? So you subtract from the first character and you add it. Okay. First go to let's see, power of 32 Is it n or n minus 1? Jeez. I think it's n minus 1. Okay, we have a small n, so let's print out this is s sub I, this is t sub I. So we have 4 characters, so it's going to be 130, 900, 27. Okay, so that's fine. Okay, I think this is right. Yeah, I think this is right. Okay, easy to do off by 1, but yeah. Okay, so for all n rotations, if and then we rotate by taking t sub I times first. So we take this, we subtract it, then we rotate it. Just in case I needed to convert this later. And then we add it back in. Okay. And then now we can see how many things. Oh, okay, 1 and 3. Okay, that's good. This is what we want. 5. Doesn't matter what the number is, I guess. Okay, so I think we're good here. So then now we have count, and then now we can set up the DP, right? So DP is equal to times k plus 1 times 2. Oops, k plus 1 is here, and this is 2, and then yeah. Okay, and then DP of 0, 0 or 0, 1 is always going to be equal to whether okay, but I guess actually I made a mistake here. This is the number of total ways, right? So this is the beginning ways. So yeah, okay. So this is either begin if it's equal to hash same is equal to true. I guess we could have just done the comparison actually. Whatever then, fine. So let's go to t. If this is true, then we start with 1. The other one is always going to be 0, because that's just how we start. And then, but if they're not the same, then what happens? Right. So then now we set up. I think I didn't do it for this one. Let's do it real quick. So then now in that case, dp0 of 1 is equal to 0, and then dp0 0 is going to be, okay, I guess that makes sense. Okay, and then dp 0 of 0 is equal to or maybe even just Yeah, it's fine for now. This is the I'm going very slow at this one, to be honest, but that's fine. And then now for let's do one. So dp of I1 is equal to okay, so good is going to, that's number of good ways is going to be equal to n. So the n minus 1 decisions, and the number of good of them is the one that gets you to the right answer, and the number that gets you to the right answer is the I guess it's just count, and then bad is equal to n minus 1 minus count. Right? I think this is a little bit off. No, that should be true. Okay. So then now, if it's good, it's equal to minus 1 of 0 is number of wrong ways times good. And yeah, plus number of good ways times good minus 1. Right? Because it cannot be 0, right? So if it's already good, it just cannot choose the 0. So I think this is the actual thing. I think I messed up on the other one, but maybe. I should have kept my brute force code, but I think I guess I know the answer for that one, but so if it's not equal, then it's going to be bad, right? The number of bad decisions. If they're bad, they're all going to be bad. Yeah, plus dp of I1. And then if it's already good, is it bad plus 1? Man, I'm really bad today. Let me just print it out real quick. My mind is not working that well. I want to get the one that I was doing, so F4 0 3 6 21 60. Is that what we have? 0 3. I did it the other way. So 1 0 3 6 21. 1 0 3 6 21. Maybe that's fine. I actually don't know. Now I'm getting a little bit lost. Let's do another one or another number. Okay, I think this is right, even though it looks ugly as hell. And then now it is just return dp sub k of 1. Right? I mean, of course we have to do some mod stuff and stuff like that. I say this, but I feel like I forget it a lot. So let's actually add mod here. And in theory we're done, but k could be really big, right? So now we have to figure out how to do this in a Q matrix. It's been a while. How to set up Q matrix? I forget. Basically now we start with I think the how many people got in so far? A lot of good amount of people. Okay, so then now we set the vector as, well, this is the vector, right? So the starting vector is equal to, that's a terrible name. Okay, fine. This is going to be equal to this is lazy. Alright, let's just do at least just do it once. Fine. Same as good. Right, and then the transformation matrix is going to be let's see, right? I always get these wrong, so I did good. And then now we have to take t to the power. Is there Python matrix power? NumPy? Is NumPy in Leetcode? NumPy? I guess we'll see. Also, using this is kind of transformation matrix. It's kind of bad, but is equal to np.matrix. Does that work? Yeah. I might have to import it. Hang on. Where is my other window? I could also just write it myself, but I am a little bit lazy about it today. It's either this or I guess like the transformation of it, so I don't think I'm that worried about it. Okay. And then now how do I do power in NumPy? Okay, right? And then okay, and then NumPy multiply matrix by vector. All right. Num dot. I in the past I've written this, but I am today not really not really in the mood for it, I guess. And I have half an hour left, which is a good amount of time, but also not quite good enough to do everything. All right, so then now print. Wait, not dot product. Oh, I guess. Oh, we could use an array. Does that work? Oh, it's just returned. Right. Alright, so that looks possible. So then now it's read.tk, maybe? And then there, is that the answer? I don't think so. Maybe it's the other. It's easy to mess up the ordering, but this doesn't look right. Is it the dot product? I don't. I feel like it's just regular multiplication, to be honest, but oh, matrix is molded. Yeah, I don't think that's right, but did I mess this up? The other thing was good though, right? It's giving me. What is the right answer again? 183.22125 is just not here. Am I doing this wrong? It's the linear combination of. Oh, I'm doing it wrong. This is no. How did I do this? I need an extra dimension. So I am doing it not quite right, for sure. This is not how you do transformation matrix, but was basically, okay, so I have 4 numbers. Well, I have 2. Okay, I see. Okay. Maybe something like this, and then now, what would my matrix look like? Alright, I have to write it out. It's been too long. Okay, so I have 0, 0, 1, 0, and then basically my output matrix should be do I need that? Is that true? Am I just maybe mispowering it? It's possible. No, still wrong. Okay, so this is good. This is 0, this is 1. I think I mixed this up. Why is this? Because I think my 0 is the different one, and then I just kind of had it in a different order. Still wrong though. I mean, this is too big, but okay, so you start 1, 0, and then the next one is just going to be good of this, good of the bad, okay, and then good minus 1. Sounds right. Bad and bad plus 1 also sounds right. So what am I doing wrong? On the matrix multiplication, do I set up count? Yeah, okay, everything seems okay. Alright, let's just do 1, right? Alright, if k is equal to 1, do I get the right answer? Is equal to 2, 3. So 1, 0 to 2, 3. Is that even right? No. But the DP is right? So after 1 it should be 3, 0. So why is my matrix? What is my matrix? My matrix is this. Oh, again, did I just like mess up the good and the bad because I am really bad? Maybe I did actually. Because this is the okay. Even silliness here. Okay, fine. Let's see. Okay. Yeah, because the 1 is the good and 0 is the bad. Okay. Wow, Larry, you are an idiot. Or a mad genius. Probably just an idiot though. Okay. I don't know how to, ooh. How do I do mod pow on this? I guess I have to implement it myself actually, to be honest. Maybe I messed up. Because I don't know that I try to do it this way, but maybe I have to do mod pow because I mean this is wrong. This is 2. How did I get that wrong? Good. My notation was pretty bad, but how? What? Is it k minus 1? Did I just mess up? Why is that giving me 6? That's not good. This is not the time to be doing that. Is it right for the other ones? Oh my. I'm wasting too much time on this. 3. It's the number of ones, right? So this is 2 is right, but this is 3 or 6, I guess actually. Why is this returning 125, 2, 2? Why is this returning 6? Because it's getting it from here. Did I mess this up? Why is this so big, in fact? Also, how is this -1? I am not knowing how to do this. Why is this so long? Oh, because it's not you go to the initial one. So 0, 1. Does that throw things off? It begins with a 1 on the wrong thing. Begins on the 1 on the wrong thing. Or it's just a good thing, -1. I think that's the way that we had it noticed, but that doesn't seem right. Right? Like if this is the same and then just off shift by 1, is that right? Oh, whoops, should be this. And then if it's the same, we subtract 1. I think that was the idea that we had, but we have 20 minutes left to try to run through this. I mean, this is right now, but I'm not super confident, to be honest. And we still have to do the, let's see, upon matrix power, mod. Mod. Okay. Alright, I guess we have to write our own mod power, which is fine. Okay, how do I do matrix modification? Okay, so how does it go again? I mean, I know how to do this, but I feel like but I feel like I need help. Oh my god. Okay. And now, yeah, okay, this is right. Yep. Whatever. Okay. And we have to mod it with mod. Okay. Where is it? Okay. How are you going to do matrix multiplication? It's a 2x2, so okay. So how are you gonna? What is it? IK? Ooh. And then we have to do a mod. Okay. And now we did the mod Perl. How do I do the back to the numpy thing? Yeah. Just numpy.away or something? np.away. Okay, do we have the right answer? Okay, it looks okay. So now let's try one with a ridiculous number. Yeah, maybe not this case. Should still give me the same answer, but okay, fine. Let's not print out this anymore. Am I giving the right answer? I think so. I guess I can just assert that this thing is equal to this thing. I mean, I have time, so I can kind of... Okay, so that looks good. Let's get rid of print statements, and I think we're... Maybe there's an edge case, but at least we've maybe solved it. Man, even knowing what I'm doing, like, this took a long time. And also we have to get rid of this, because that will time us out. Okay, and then now let's do the big case. So we're just checking out the timeout. Okay, so let's give it submit. Oof, oh. Huh. I don't know how to get that number, but... Did I mess up the mod somewhere? That number looks so weird. Did I use that number anywhere? Why is that? Oh, because I assumed that they can match. I knew that this was the case, but then, but I kind of forgot it because we were doing so much other stuff. All right, let's give it a submit again. Fingers crossed. Oh man, off by 2. That is actually the worst. Okay. I don't know how to solve this then. Or maybe it's just kind of Maybe my subtract by 1 thing is a little bit weird. I mean, for sure it is weird, but okay, so it has count as 2. N is equal to what? At 15 minutes, this is not looking great. 10, and you have 2. Maybe this thing isn't quite. Yeah, I really didn't think this felt good, to be honest. But like by hack with -1. But I don't know why my thing is wrong though. So all right, well, you have to figure it out in 14 minutes. So this is actually a difference, but I thought that may be the case, but I guess I was wrong. Okay, so I think I have to bring back this DP real quick, and then because we could get the answer for this anyway. We'll just have to take out this case. And also this other case. Alright, is the DP right? The DP is correct. So how do we fix the DP? What did I put? Tell me why. Oh, whoops. Okay, so this is the. Oh, this is for Q. This one. How do I do that? Why? 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 I thought this would be right though, to be honest, but. What is the answer for this one? 183, but we return 182, is it? No, that doesn't make sense. Oh no, I'm looking at the wrong one. So this is the second case where this is returning. Why did I not get? Why is that so wrong? Oh, is it because I messed up on this? I think this is where I wasn't sure, but then I got lazy. Or I just was focused on other things. Yeah, I just messed up the matrix. I don't know what I'm printing anymore. There's so many prints. Okay, that's. Okay. 7.2. The assert is now true, I think. So. Okay. I did try to fix that particular part, but I just forgot about it. What is the answer? 5.4. Okay, so we're Gucci. We have to get rid of one print statement somewhere. Alright, here, I guess it's only one per problem, it's fine. I knew okay. I mean, it was, I don't know how people got it so quickly, to be honest. Okay. I mean, anytime you finish all four, especially for anytime you finish an eight pointer, you know, I'm gonna feel good about it. But Oh yeah, shout out to Love Jenny, our very own Just Gia. Don't know how he did it, to be honest. Maybe I'll ping him. I'm just so, I mean, the quickly part is to, I mean, maybe there was a template, or maybe people have seen it before. I don't know. I mean, it's still very fast. I mean, well done. 21st. The 4 wrong answer on this one, it hurts though. Hurts to watch because it went top 6 without 4 wrong answers. But I don't know. Any other shoutouts? Let's see. Don't know if I see anyone. So let me know. Let me know if you want me to shout you out. Let me come to our Discord and kind of just take a look. I didn't finish the top 100. I think that's okay. I mean, I have so many wrong answers. One of the wrong answers was silliness. What was one of the wrong? Oh yeah, I mean, that one, and the other one was silliness too. So I guess I should have gotten it without wrong answers if I was smarter about it. Seems like 130 something. My first 3 Q is so fast that just getting this one is not let me jump that much. I do wonder if there's I don't think there's a easier way. I think the DP would have been pretty straightforward to do. I spent it way too long. I spent it way too long on brute forcing and trying to find an easier pattern, to be honest. When maybe I should have just written this out. I knew kind of, like, I mean, it still took a while, but I knew the idea pretty quickly, so yeah, thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Stay good, stay healthy, take good mental health. Hope you enjoyed the contest. I'll see you later and take care. Bye bye.